Welcome to our third lesson of our module 2, and in this lesson we are going to be looking at the equations as well as the network connections for various type of faults that you get. So we've got faults that are happening on our unbalanced system, and they usually are called either a shunt type of fault or a series type of faults. So your shunt types of faults are divided into four. You've got what you call a single line to ground, a line to line, a double line to ground, and a three-phase with or without an earth. And then you've got your series type, which is your single phase open circuit and a cross country fault. So the first line that we're looking at is a single line to ground fault, where in the diagram that you're seeing, you can see that on the first phase, which is your phase A, you have got a fault that is happening at that point. So once your fault happens, we can state our VA will equal to 0. Our currents in my IB and my IC will equal to 0. And where my fault current will be occurring is going to be where the fault point is happening at. At the bottom, we are showing what our positive, negative, and phase sequence networks are doing in a single point to ground type of fault where they get connected in a series format. So if you're looking then over there, you'll see that your VA is going to be your V naught plus VA1 plus VA2, and therefore your V naught is actually equal to minus ZOIO, and this you see from this bottom figure. And your V1, you can see that you've got a V there which is showing as 1 at 0 degrees, and then you will subtract your Z1I1 to get your V1, whereas your V2 is just your negative Z2I2. So if I had to add my V naught, V1 and V2, I know that I will be having a 0 because they are in series. I can utilize Kirchhoff's law. Then that can equate for me to be able to work out what V1 is in terms of the other two voltages. And knowing that my current is going to be I1 is the same current flowing throughout equals to I2 equals to I naught. I can then assume, knowing that now that equation is going to be a third of IA. And therefore my I naught is simply going to be V over my Z naught plus Z1 plus Z2, which is our total impedance of the system, and that will give me all of my currents that are flowing in that system. So on this one, we're looking at a line-to-line type of fault, which is happening between two phases. Normally, when you have a flashover in your system, you have that. So your phase sequence will consist of only a positive and a negative phase sequence, not a zero phase sequence, because there is no earth or ground involved in this type of fault. So therefore, then the two will be shown as parallel, and then you can be able to work out what your current one is, whereas it is the voltage drop across your Z1 in series with your Z2. So I1 becomes that V divided by Z1 plus Z2. Then calculating the voltage drop, the sequence voltages can then give you that you've got your V1 equals to your V2 because it's a parallel system. And you can also state that your V2 is equal to negative Z2I2 from the diagram. Then your next fault is a double line to ground fault. Now this is happening between two phases and there is a ground involved in that system. So your phase sequence will thus consist of all three of your phase networks. That means you'll have a positive, a negative, and a zero phase sequence network, and they shall be connected in parallel. And so there you can see the connection in parallel. And therefore here I can summate that my I1, I2 and I3 will equal to 0, and that my I1 is actually equal to the negative of I2 plus I naught. The current I1 is the voltage drop across my Z1 and the combination of Z2 and Z0 in parallel. So how do I write that out? I will say that my I1 is actually equal to V divided by Z1 plus my Z0 and Z2 in parallel together. And then I know that my voltages for all of my symmetrical ones, they will be equal to each other because I've got a parallel system, which will equal to 1/3 of OVA. And then in this case, we are going to have your fault that occurs between all of your phases. So it's a three-phase type of fault. And because this will then mean it's a balance fault that is happening on all three phases at the same time, it means that it does not become a symmetrical component type of a fault. I'm only going to have a positive phase sequence happening in this type of a fault. So I usually normally use my normal Ohm's law to work out what my currents and voltages are going to be. Then when we've got that three-phase fault with a ground, you can see that I've got here how my voltages are going to be in this situation. So what is important from what we have just explained is that in a balanced three-phase system where you don't have an earth fault, then you're only going to have your positive phase sequence result. Then in a three-phase or three-wire system with no earth fault, but supplying an unbalanced load, then your currents will be positive and negative only in sequences with no zero sequence. But then in a three-phase system where you do have an earth start point, then your currents will result in all three of those components networks. Then we look at our series type faults. So we had two of the series type faults. It was your single phase open circuit first. And this, as you can see on the picture there between P and Q, you actually have an opening that is happening on the top phase, which is our A phase. So when you have an open circuit that occurs in that scenario, then you will know that your IA equals to 0 and your other voltages are going to be equal to 0. So you are going to have a voltage that is going to show as your fault between those two places where the open conductor is had. So at the bottom, we're showing then what our phase sequence voltages are going to be, where V naught is equal to V1 equal to V2 are all equal to a third of VA. Then we look at what we call the cross-country faults, and really these type of faults are saying that you can have any of those shunt faults we described before, but the difference is that more than one occurs in the same network. So it could be a line-to-line fault happening at a certain place, and then another one further down happening at different even phases that could be happening at. So as long as it's multiple faults that are happening within that same network, we call it a cross-country type of a fault. Then this is the summary of all the faults that we're looking at, and you can see that on the top I've named all of them, the shunt as well as the series type faults, and it really shows that what would happen if you had a ZF present. Okay, so when they go to ground, they go via another impedance to ground, so it would be a star connection type of a fault. And you can see what our zero, positive and negative phase sequences or impedances rather would be looking like. I have put in a couple of examples for us to demonstrate the shunt type of faults. And on this first one, it basically gives you Z0, Z1, and Z2, where you are asked to compute and calculate the voltages and currents for a three-phase fault. So looking now at the next one where they say they want us to calculate a line to ground fault. So you've got exactly the same impedances that you've had before. Now in our formulas, we know that all our phase sequence currents are going to be equal, and that our V naught is equal to that V, which is really that one, not V1 necessarily, guys. It's that one at 0 degrees divided by the total of all your impedances. So you get what I naught is. Once you've computed I naught, you can be able to compute what your IA, IB, and IC are, and then you can move from that point in order for you to go compute what your V naught, V1, and V2 are going to be. And you know that your V naught is simply going to be your minus Z naught I naught, whereas your V1 is going to be your V, which is that 1 at 0 degrees minus our Z1 I1, and then our V2 is minus Z2 I2. Now that you've got those, you can go and work out what your phase voltages are, which is my VA, VB, and VC worked out at the bottom. Then when you get your line to line type of a fault, it means that you can go again and work out what your currents are going to be in that system. And we know that in this system, your I1 is equal to your negative I2. So if you go and work out what your I1 is at first, you can then be able to see what your I2 is. Then that will take you for you to be able to work out what your phase currents are for that system. Once you work out the phase currents for that system, you can start working out then what your V1 is going to be. Because you don't have a zero phase sequence network, by default your I naught was 0, and therefore your V naught is going to be 0. So we're only dealing with your positive and your negative phase sequence in this case. Your voltages then V1 and V2, you can go and put in the values for them. Then your phase voltages get converted into VA, VB, and VC utilizing your sequence voltages that you had in order to work out what your VA, VB, and VC are going. We then look at our double line to ground fault, or line to ground fault. And in this scenario now, we know that our I1 will equal to, I don't like this thing that keeps saying V1. It's not V1, guys, it's V. Okay, you can say V fault, VF. V over that Z1 plus your Z0 parallel to your Z2. Once you've worked out I1, then you go and work out what your I2 value is going to be, which is your I1 multiplied into Z0 over Z0 plus Z2, and then you go work out what your I0 is, which is the other way around. It's I1 multiplied into Z2 over Z0 plus Z2. Then you can be able to go work out what your actual V1 is. That's why I don't want us to say that one was a V1. It's a VF, which is your fault voltage. So this one is also is a V1 is equal to VF minus I1 Z1. All right, so which is then that V1 is going to be 1 at 0 degrees minus whatever my current was that I worked out as I1 multiplied by my Z1 that I've been given.